Okay, guys, can you guys hear me? Okay, guys, can you guys hear me? Okay, so let's give it maybe 2 more minutes before we get started. Today is the first lecture for the new session. We always have some technical issues, especially for the new students. So let's bear with us 2 more minutes and then we'll get started afterwards. All right? It's pretty common for the first lecture, a lot of students, they have some technical issue. So that's the reason I keep telling your parents, especially for the first lecture, you better be here at least 10 minutes, 15 minutes earlier in case there's any technical issues. Okay, so maybe 1 more minute, we will get started. All right, so let's get started. So welcome guys, welcome to our new session. This is our session number 3, the 2D geometry. So before we get started, as a common practice, or we can say as a cliche, I'm gonna say that one more time, some basic information, because every time we have some new student joining us, maybe roughly 5 minutes, let's do something fairly quick, okay? And this is a short and brief introduction for our lecture. Okay, so at the very beginning, I want to emphasize the importance of this interaction, right? Interaction is always more than important for all the lectures. These days, due to the COVID-19 situation, you guys should be much more familiar with the online lectures than otherwise, right? So that being said, so you might see more opportunities, students and teachers, they're interacting over the internet. So I personally suggest you guys, you can turn on your camera. So, this is making more formal as a real lecture. So the students can see the teacher while the teacher can see the students. As long as you have this eye contact, sometimes it's actually easier for everyone to pick up each other's opinion, right? And you have actually 2 ways to have this interaction with me. The first one, which is the most recommended, you can just directly unmute yourself and directly ask me questions. During the entire course of the lecture, I'm going to be keep asking you a lot of questions. So unmute yourself and directly answer my question. Or if you find in the middle of my lecture something is a little bit confusing, you want some more explanations or clarifications, you can always unmute yourself and ask me the question directly. Well, the second way is actually you can chat with me. I assume you guys should be very familiar with the Zoom application. But for the guys that are not so familiar, what you can do is in your control console, there's actually 3 dots in the very right, more, right? You click that option in the drop-down menu. The first option will be chat. You click that option, it will bring you to the chat board. You have 2 ways to chat with me. The first option, or by default, is you chat to everyone. So that being said, your questions and your answers will be seen by pretty much everyone for the entire classroom. Or if you feel a little bit shy or you're not so comfortable sharing your information with pretty much everyone, you can chat with me individually. So that being said, from the two option, you click that arrow, right? You'll be able to see a drop-down list. You can click my name. So that being said, this is going to be a private chat between you and me. Your answer or your response won't be seen by the other students. Okay, but you know what? I'm here actually to help you guys rather than to judge you guys. I assume that's pretty much the same for every student. So don't be shy. You can post your answers to the group chat and everyone can see it. The second part is the homework. Every lecture, we're gonna give you guys 3 homework. I believe the homework is actually a very important part. It works as an extension for our lectures. And our homework are actually specially designed. We actually pick up the homework which gets aligned with the sample questions that we introduced during the lecture. So as long as you're doing the homework, this can be considered as a reinforcement of what technologies or like all the concepts that we introduced during the lecture. So please try to put more emphasis and more focus for the assignment. This can be considered as an extension and rehab of our lectures. Number 3 is, okay, this is actually the language. So language, our lecture is pretty much in English. So this is like a unilingual language. And a long time ago, our lecture is actually bilingual, English and French. But unfortunately, these days, less than people, they can speak French. So pretty much everyone speaks English. And my personal experience is that whenever you have a meeting with pretty much everyone, as long as there's only one person who speaks French, who speaks English, excuse me, so everyone has to switch into English, right? So that being said, no problem. Our lecture will be focused in English. Not a big deal, okay? And the last one is the presentation. I believe this interaction is always more than important. So there are 2 ways for actually offering guys to have this interaction. And one is the lecture, the questions, so on and so forth. And second part is the presentation. Presentation actually can be classified into 2 parts. The first part is actually based on the homework. Every time I'm going to be marking your homework. And as long as I find you do the good job for your homework, in the next lecture, I will be asking you to present the homework to all the students. But again, this is not compulsory. They're based on your comfortable. If you feel a little bit uncomfortable or you're a little bit shy, always let me know and I'll skip for the next time. All right. And the second category of this presentation is that every time from the second lecture, I'll be asking one student to give us a quick presentation to find out the problem and give us a quick presentation. So this problem can be whatever problem you can find it on the internet, or maybe something from different math competitions, or even from homework. As long as the problem you believe the content is pretty related to our lectures, you're more than welcome to present this problem to all the students. Well, the most important thing I want to take this opportunity during the presentation is that I want you guys to show us the way, how do you think? Because these days, if you want to go to the top tier tech companies like Google, Amazon, Facebook, so on and so forth, rather than the code interview, they always want you to use the whiteboard. So think aloud. Not only know something inside your head, you have to speak it out, or you have to really present it to all the students, right? So I totally understand Rome wasn't built in a day. So it might take several years for you guys to really pick up such a presentation capability. So that's the reason I'll take this opportunity. Hopefully every student, you can, try to be more dynamic, try to be more autonomic. As long as you have, I ask you to do the presentation, try to get involved as much as you could. All right, I think that's a short and brief introduction for our, the organization of our lecture. You have any questions? All good? All right, if all good, so let's get started. Let's go to the real part of today's lecture. This is our lecture about the geometry part. So geometry, I gotta say, this is like a killer for the North American math competition, a killer. Pretty much like, like the Simon Cowell in American Got Talent. He always give you a lot of challenging questions, always make you a little bit sad. And like, if I make like analogy, we have like the kidney stone, right? It means like the urine cannot go through. Sometimes we have like the gallstone, right? Like the bile cannot go through. So as long as a lot of students seeing the geometry, it's pretty much like the brainstorm, like the solution cannot go through. And why does geometry is like so challenging? I think there are a lot of reasons behind that. One of the reasons is actually our lecture, our in-school like curriculum. Long time ago, when I say long time ago, pretty much like more than 20 years, 20 years ago, like the Canadian and American in-school curriculum, we actually put a lot of focus for the geometry. However, due to this kind of like organizational changes, this migration, so on and so forth, gradually by gradually, our current lecture, especially in school, they put less and less focus for the geometry. So think about your real lectures from your day school. Maybe the teacher doesn't put so much focus, especially, right? Especially our day school, we don't put a lot of focus for the geometry. So this is actually one part why students are kind of weak for the geometry. And second part is geometry really needs a lot of like, what should I say, like talent, if I use the word talent. Some students is very good at algebra or even at some other branches. However, they feel a little bit challenging for the geometry. So kind of the reason is because we do not have a very organized introduction about all the concepts, all the theorems in the geometry. So that being said means leaving the student a little bit helpless during the math competition. So in our lecture, we're trying to give you guys a more overall summary. We're trying to give you guys more, what should I say, like well-organized summary for all those important concepts for the geometry. We're going to introduce guys pretty much all the important theorems. We're going to also introduce guys very important patterns. In the geometry, the patternized solution is very important. As long as you see a specific shape, then using a conditional React, you should automatically find out a solution. There are always some like patternized solution for specific shape. So we'll take this opportunity in our lecture trying to give you guys a summary how those patternized problem looks like. And then hopefully at the end of the lecture, you can use all those patterns to fill up all, what should I say, to really help you guys to create such a talent, right? Kind of like a conditional React. So in the future, if you see something similar, it becomes so straightforward for you to directly think of the solution and find out approaches. All right. So talking about the geometry part, generally speaking, I think geometry only contains three major things. Three major topics for geometry. The first one is segment and the length. This is like a big direction. You see, a lot of problems, they ask you to either calculate the length of a segment or prove two segments that are in the same length, or two segments that are like one is proportional to the other, or kind of like like the ratio relationship. So pretty much these are all topics regarding the segment and its related lengths. The second part, geometry focuses on the angles. You see, a lot of problem trying to determine what is the measurement of an angle, or try to prove several angles that are either equal to each other, or one is a specific, like a specific multiple of the other, so on and so forth. So this is actually the second big category. The third big category is actually area, right? As you can recall, in most of the math competition problems you saw before, they might be asked you to determine the area of either a triangle or some quadrilaterals or some circles, so on and so forth. But they're basically focused on those area-related things, right? And actually, think about it. Between these three topics, which one is the most challenging? If you can do a quick guess. Angle, segment, length, and the area, which one actually needs more inputs, more energy than the other two? Pretty much area, right? Because area is actually a combination between the pretty much like the angle or the segment and so on and so forth. So that being said, for our lecture, we're going to give you guys some very interesting focus on the area. And also there's another very important reason why we want to start our lecture talking about the area, because area method, or what should I say, how to determine the area of the different shapes is actually a hot spot for the North American math competition. In order to justify my conclusion, I'd like to give you two graphs, two pictures. The first one is here. I actually did some statistics. I traversed all those problems that has been tested in the North American math competitions in the last 20 years and actually summarize and classify all the problems one by one. I really like to calculate which problems are the most important and most high frequently tested during the math competition. And this is what I actually come out with. The first one is actually, you can see a problem statistic for the Euclid exam from pretty much like last 20 years, right? You can see the #1 ranking, the most highly frequently tested exam, like the problem is actually geometry, area, and volume. This is actually takes more than 30% of the entire problems. I'm talking about all the problems in the last 20 years. So you can see area is very important for the Euclid. And same thing applies for the COMC. The #1 important is a kind of like circle property, while the #2 is actually the geometry, area, and volume. Also roughly almost like a 1/4. So that being said, for the Canadian exams, if we're talking about not only the geometry, but also the entire math competition, area and the volume is the #1 important. So for sure, we're gonna spend more focus on this topic. Okay, this is for the Canadian exams. Then what about our famous American exams? I actually did the same thing, so I'll show you the result. There you go. This is the same thing. As you can see, AMC10 and AMC12. All the problems do a statistic for the last 20 years. As you can see, for AMC10, the #1 important is actually area. It takes actually more than 30%. For AMC12, pretty much the same thing. #1 is also area and volume. And check it out here. The weight is actually more than 40%. So that being said, the American exams actually takes more emphasis on the area method than the Canadian exam. So I hope, because our lecture, this is like the Hawk lecture, right? Our Hawk lecture is pretty much focusing on the AMC12 and the Canadian, like Euclid, COMC, AMY, all those kind of a high-level exam. So nevertheless, what kind of exam you want to go, you can see that area method is actually very, very important. So that being said, I really want to start our geometry lecture. Let's try to focus on the area method. Let's try to do some summary. What are the most important AMC? What are the most important problems that will be tested for all those kind of math competitions? And then we can actually get started. Okay, so while we're talking, some students asking a question, why the weight percentage add up more than 100%? That is very good, because sometimes one question, it tests you multiple knowledge concepts. Maybe a problem they test you the area method, they also test you some like a number theory related, right? Some factorizations, maybe some linear function related stuff. So that's the reason the same problem might have multiple concepts. So you add up together, might be more than 100%. But nevertheless, you can see area is actually #1 important. All right, so far so good? Okay, if we're on the same page, let's get started to see how we're gonna have some summarize for all those area method. So this is our #1 topic I wanna talk about, the different ways theorems in area calculation. Okay, I'd like to give you guys some summary, what kind of formulas you need to know for the area related problems. #1, we have a triangle, A, B, C, A, B, C, this is HA. Then for sure, if I ask you to determine the area of the triangle, area ABC will be equal to 1/2A, HA, 1/2B, HB, 1/2C, HC, right? This is like the basic thing. As long as you know this, you'll be graduating from the junior kindergarten, right? You should be able to know this. So the only thing is, as long as this is a acute triangle, the height is actually inside the triangle. If this is an obtuse triangle, the height might be outside the triangle. Okay, this is number one. Number two, pretty much the same thing. Triangle ABC. So we're going to have triangle ABC will be equals to, this is A, this is B, this is C, 1/2 AB sine C, right? 1/2 AC sine B, 1/2 BC sine A. Is that right? This is the second way how to determine the area. So that being said, instead of really calculating the height for a specific bottom, you just directly use the sinusoid, right? Because this is HA. HA can be considered as what? C times sine B, or B times sine C, right? As long as you know this, I think you can graduate from the senior kindergarten. Okay, so number three, these are pretty easy stuff. I just want to give you guys a quick summary. It's the famous Heron's formula. Heron's formula says what? If you have a triangle ABC, the three sides is A, B, C, right? Instead of calculating what is the height, what is the sinusoid, you can directly determine P equals to A plus B plus C divided by 2. And as triangle ABC, the total area of this triangle ABC can be written as P minus A, P minus B, P minus C. Is that right? I think this is a pretty, for me, this should be a very familiar formula that you see from time to time. That being said, as long as you see the three sides of a triangle is given by the problem, instead of calculate the area, like the height or like the angle value, the most straightforward way is directly determine the area of the triangle using three sides, right? This is actually how you're going to determine the area of this triangle. But I gotta say, this way actually always involves a lot of calculation, right? Because you have to basically get full terms, calculate the multiple of the full terms, and then do an under root. So the calculation is highly involved. But I think the formula per se should be very straightforward, and you can remember this fairly quick. And how to prove this Heron's formula? The proof. So actually, you can prove it by different method. If you type like how to prove Heron's formula from Google, you can find out more than 100 different methods. But generally speaking, you can actually using the Pythagorean theorem. That's, I think, the most straightforward way to prove the Heron's formula. Okay, so I'll just leave it as a homework. You guys can actually do some Google search, figure out how to prove this Heron's formula. Okay, so far so good. All right, so let's continue. Number 4, actually, during this area method, I actually did some analysis for all the problems previously. I find out not only we just determine the area using the formula we introduced previously, there are some other theorems that are highly combined or highly related for the area-related problems. So that being said, a lot of problems, as long as they ask you to determine the area, you're probably going to use some of these following theorems. So I want you guys to basically pay attention to these theorems. So I'll help you do some conclusion. The first one is the very important bisector theorem. So what is a bisector theorem? Something like this. You have a triangle ABC. You have a bisector AP. So it means these two angles are the same. BAP angle is equal to CAP angle. Okay? As long as you have a triangle and you have a bisector of the triangle, then automatically you should be able to have AB over AC equals to BP over PC. As long as you see a triangle the triangle has like a bisector for any kind of angle inside, then automatically you should have such a very important theorem. AB over AC will be equal to BP over PC. So trust me, this is very important, and it will be tested by AMC every single year without any exception. Okay, so let's have a look how to prove this problem. Okay, how to prove such a theorem. Actually, to prove the theorem, we just basically use all the technologies we just introduced so far. We only introduced 3 different technologies, right? We're pretty going to use them to prove this. So let's check it out from here. So now we're basically having a big triangle and they're split into 2 small triangles using our bisector. Then automatically you can see that this triangle, the black one, and the red one. Let's have a look. What's the relationship between these 2 triangles? The area of triangle ABP, if I want to do a ratio to the area of triangle APC. How to determine the area ratio between these 2 triangles? I think intuitively, you can use the theorem that we just introduced using our sine, pretty much like the sine law, right? The 2 sides and the sinus value of their included angle. So let's check it out. So the first triangle's area will be 1 over 2 AB, AP, sine BAP, right? The second will be the same, AP, AC, sine CAP. Is that right? Because the question says what? This is actually a bisector. So that being said, these angles actually have the same value in measurement. So that being said, these 2 sinusoidal values can be crossed out, right? What else? AP can be canceled out. 1 over 2 can be canceled out. So if I do some simplification, this ratio becomes what? AB over AC. Okay, AB over AC. Pretty much this guy over this guy. This is actually one way to determine the area ratio between these 2 triangles. And what about the other way? Is there any other ways for us to determine the area ratio for these 2 triangles? Yeah, for sure. I have some students give me the answer right away. Because these 2 triangles, they are sharing the same height, right? This is the same height. So the areas ratio will be exactly the bottoms ratio, right? So at the same time, triangle ABP, triangle APC, they have the same height. So 1 over 2 height BP, 1 over 2 height PC. This guy will also be BP over PC. All right, so that being said, means AB over AC equals to BP over PC. So that's actually our conclusion for this problem. You see, it's very straightforward to determine 2 triangles that are sharing the same area. So that being said, you'll be able to have this bisector theorem. All right. So most of the textbook stops from here, saying that, okay, that's pretty much the bisector theorem, and we're good to go. Today, I'm going to give you guys a little bit expansion. Actually, the one what I'm showing you here, it has another prefix for the name. This is the internal angle, not angel, angle. This is the internal angle bisector theorem, right? Because you're basically do a bisection for the internal angle. As long as you know you've seen the name internal angle, then intuitively you know that there might be an external angle, right? And that is actually true. So I want to tell you the second part of the theorem. We call it external angle bisector theorem. I think I barely see any textbook talking about this part, but I think it's also very important. Let's say you still have a A, B, C, right? You have such a triangle. This time, instead of creating the internal angles bisector, I'm going to do a external angles bisector. Let's say this is T, okay? I want to say these two angles are the same. That makes sense, right? And then all the way, it intersects the extension of BC size at the Q point. Okay? You know what? Luckily, you will have exactly the same form. You will have AB over AC equals to BQ over QC. AB over AC equals to BQ over QC. Okay, so let's check it out. How are you going to solve this problem? It's actually something fairly quick. Again, if you know what we did for our internal bisector theorems proving process, we basically find out what? What is the area ratio between two triangles? This is going to be exactly the same for the external bisector theorems proving process. Let's check it out from here. So let's try to determine the area of ABQ and the area of ACQ. ABQ is actually what? The big triangle, right? This is the big triangle, ABQ. It will be 1 over 2 AB AQ sine BAQ, right? ABAQ sine BAQ. Then what about this ACQ? ACQ is here, this red triangle. Again, using the second rule that we introduced, 1 over 2 AC AQ, and I'm going to do something like this, right? But this can be considered as what? Sine 180 degrees minus BAQ, is it right? 180 degrees minus BAQ. This is 180 degrees minus BAQ, and this guy is the same as this guy because we're talking about an external angles bisector. Is that right? Do you guys familiar? Are you guys following this? The upper part is exactly the BAQ, while the lower part should be AC times AQ sine this angle. Sine this angle is the same as sine this angle, right? Because these two angles are exactly the same, right? And this one can be written as 180 degrees minus BAQ. Okay, if you're familiar with the basic trigonometry identity, these two parts are actually the same, right? Sine theta is equal to sine pi minus theta. Is that right? So that's a basic identity for this trigonometry. So that being said, this part can be canceled. So that one will be what? AB over AC. AB over AC. And also, same thing, these two triangles, ABQ and ACQ, the blue one and also the red one, they're sharing the same latitude, right? So the areas ratio will be exactly the bottoms ratio. That one will be what? BQ over QC. So that one give you exactly the same thing. AB over AC equals to BQ over QC. All right. So if I like to consolidate this external and internal two bisector theorems all together, I'm actually having something like this. Let's check it out. This is actually the interesting part. This is the external one. This is the internal one, right? A, B, C. So let's say this is P, this is Q. So that being said, these two internal, external can always be put into such a way. AB over AC equals to what? This is AB, this is AC, equals to from B all the way to the intersection point. B to intersection point. And intersection point to C. See? The first one, AB over AC, B to the intersection point, which is P, and the intersection point to C, which is PC. This is our internal scenario. If we want to go to the external, same thing. B all the way go to the intersection point, and then intersection point going back. So that one being said can be BP, BP over PC, or BQ over QC. All right? So that being said, these two formulas, they can actually be consolidated into one single formula. They are following the same appearance, right? The same pattern. All right? So far, so good? Here I want to have a quick note. Quick note. I have no idea whenever you guys learn this at your day school, the bisector theorem, does the teacher teach you something like this? As long as you see a bisector of an angle, as long as you see a bisector of an angle, your first reaction is the points actually on this bisector will have the same distance to the two sides of the angle. Is that right? An angle A, B, C, BQ is the bisector. As long as you see a point Q is on the bisector BQ, then automatically AQ will be equal to QC. Is it right? Yes or no? May I have some feedback? Do you guys know this? This should be something very intuitive, right? Okay, this is what your day school teacher teach you, and you guys want to know this, okay? However, trust me, in the math competition, this is almost useless. In my experience, after I analyze all those math competition, not even a single problem testing you that the point on the bisector, it has the same distance to the two sides. Of course, this is a true conclusion, but it never ever tested. However, on the contrary, trust me, in the entire math competition, in the North American math competition, as long as you see bisector, your first reaction should be this bisector theorem. Okay, trust me, as long as you see bisector in any kind of North American math competition, your first reaction must be this bisector theorem. Okay, bear in mind, this is extremely important. Okay, so far so good? Okay, let's continue. So we're trying to do some summary before we jump to some real problems. Our lecture is actually organized in such a way, we always give you all the very important tools, theorems, strategies, and then we're going to use some real problems from North American competition or like the Chinese or different like a international math competition, put them together, help to justify and help to use the theorems that we just introduced. All right, this is actually our technology number 4, bisector theorem. Let's go to number 5. Number 5 is the famous sine law. Sine law is something like this. You have a triangle ABC. This is A, B, C. Then automatically, you should know that A over sine A equals to B over sine B equals to C over sine C also equals to AB to the area of triangle ABC. AB, like this. Okay? they can always be put into this. This is how, like this, area can get involved in the process. And to prove this is actually very easy. You know, triangle ABC, area will be 1/2 AB sine C, right? As long as you know this, you'll be able to basically prove this. You just try to do some rearrangement to the two sides, right? Just divide 2 times the area of triangle ABC, you'll be able to get what you need. So sine law also have a relationship with our area method. Okay, try to remember this. As long as you know the sine law, the next one will be what? Cosine law, right? They're so related, it's pretty much like a conditional react. Number 6, cosine law. Cosine law goes like this. A, B, C, A, B, C. Cosine A will be what? B square, C square, minus A square, 2BC. Cosine B will be A square, C square, minus B square, 2AC. Cosine C will be A square plus B square minus C square, 2AB. Right? These are the cosine law. How to remember the cosine law? The cosine law is kind of long, right? It has like a bunch of numerators and denominators. Is there something fairly quick for you to remember the cosine law? So I basically think about it, you can say something like this. You never get what you want. This is like a trick for you to remember the cosine law. You never get what you want. For instance, cosine A. So you're trying to determine the cosine value of A, right? So if you're calculating cosine A, you have to subtract A. You can't have A for the numerator. And also for the denominator, there's no A. It's only B and C, right? Same thing, if you want to determine the B value, cosine B, so you have to subtract B square for the numerator. And for the denominator, there's only A and C without having B. So that being said, you never get what you want. You want B, then you need to subtract B from the numerator, and there's no B's for the denominator, so on and so forth. Same thing as our life, right? You never get what you want. Like the Murphy's law, shits happen all the time, right? All right. So this is our number 6. Let's go to our number 7. Our number 7 is like the famous Pythagorean theorem. A squared plus B squared equals to C squared. Pythagorean theorem. This is actually super easy. But one thing I want to make a quick note. Pythagorean theorem is actually for what? For the right triangle, right? Right triangle. A, B, C, right? A squared plus B squared equals to C squared. This is actually the way how do you determine this is a right triangle. And actually in AMC and the Canadian exam, they keep asking you how to determine the acute triangle and obtuse triangle. So what is the rules for the acute triangle and obtuse triangle? Who can tell me what is the determination rule for the acute and obtuse triangle? This is kind of like interaction. If you know the answer, type it and shoot it into the group chat. So some students say they have an angle greater than 90 degrees. Yeah, for sure. That's the definition for the obtuse or acute triangle. That's for sure. Yeah. So, but that's pretty much focused on the angles perspective. If you do a comparison between what we just introduced here, this is actually what? This is actually using the size to determine the shape of a triangle, right? So if you can do the same thing, do a quick analogy and try to expand it, you'll be able to see for acute triangle, a square plus b square will be what? Will be greater than c square. For the obtuse triangle, a square plus b square will be lesser than c square, right? So how can I understand this? If I try to, this is exactly the right triangle, right? If I try to make this, what should I say, like this angle a little bit smaller, so the two sides will be shrink a little bit, right? The two sides will be shrink a little bit. So this is going to be A, this is going to be B, and C will become a little bit bigger, right? So A squared plus B, like a little bit smaller, like a little bit smaller, right? So A squared plus B squared will be kind of like smaller, kind of like greater than the C square. So that being said, you create like a cube triangle. Then what about obtuse triangle? Obtuse triangle, you're doing something like this. The C becomes a little bit wider, right? So A squared plus B squared will be lesser than your C squared. So this is actually from the size perspective, how to determine the obtuse and the cubed triangle. Okay, so far so good. And another way how to understand this, you can actually use the cosine law, right? Because the cosine law can actually be written like this. If cosine A is actually lesser than 0, of course, B squared plus C squared will be lesser than A squared. Something like that, right? That will be a obtuse triangle. You can basically understand the same concept from two different perspectives. Okay, this is our conclusion number 7. Let's go to conclusion number 8. Number 8 is the famous spread angle theorem. What is a spread angle theorem? Let's say I have a triangle ABC. This time I do not have a bisector. This is just kind of like a segment, right? You basically you find a point on the BC side, do a connection between A and B. Okay, this is like what I say alpha. This is beta. The two spread angles, right? Alpha and beta can be considered as spread angles. Then automatically, let's say BAP equals to alpha and CAP equals to beta. This is pretty loose condition, right? Nothing really special. Then automatically you should have sine alpha plus beta over AP equals to sine alpha over AC, sine beta over AB. This is the famous spread angle theorem. Sine alpha plus beta is actually basically sine BAC, right? This is BAC. Over AP, AP is the line which cuts the BAC angle. That part will be equal to sine alpha over AC. AC is not its adjacent side, it's actually the other side, right? Alpha over AC. Beta over AB. Not the adjacent, but the non-adjacent side. Okay? This is actually the famous spread angle theorem. Actually, to prove this is very straightforward as well. What are you going to do? You can just basically do this. Because 1 over 2 AB, AC, sine BAC can be written as what? 1 over 2 AC, AB and C, excuse me, ABAC, ABAC, sine alpha plus beta, right? Sine alpha and beta can be written as what? Sine alpha cosine beta cosine alpha sine beta, right? And then try to use some and then try to use some trigonometry-related identities, replace all those cosine using sine, you'll be able to figure out this problem. This is the big direction, how to solve this. Going to involve some trigonometry-related calculations, and you'll be able to get what you need. So this is the number 8 important formula that you need to remember for the area side. Sometimes these formulas are involved into the area calculation. Okay, so far so good? Okay, if all good, let's continue, right? Number 9. You see, number 8, we're talking about what? You have a triangle and you find a point P on the BC side. You basically do a connection, you can construct such a spread angle, right? And number 9 would be called reversed spread angle theorem. What is a reversed spread angle theorem? Something like this. If I have an angle BAC, angle BAC, okay? I find there's another ray AP. Okay, it's a ray from this angle. Okay, you have an angle and you find a ray inside the angle, which is quite doable, right? And you find 3 points. You find 3 points. Let's say B prime, P prime, C prime. On the ray side. It is quite possible, right? You find 3 points. Okay, if after your connection, C point is here, right? After you do a connection, C is here, C prime, right? You connect B prime, P prime, C prime. If you can find out sine alpha beta, alpha plus beta equals to AP equals to sine alpha over AC plus sine beta over AB. Okay, this is exactly our condition previously, right? This is our spread angle theorem. However, if you have an angle, this angle, you have 3 sides, right? You have a spread, you have a ray inside, and you have 2 sizes for the 2 rays. If you find 3 points, you can make sure these sine alpha plus beta over AP prime, sine alpha over AC prime, and then plus sine beta over AC prime, AB prime. If you can find such a relationship between these 3 terms, then you can see D prime, C prime, P prime. The 3 points are collinear. So these 3 points will be collinear. Okay? So let's do a comparison between this spread angle formula and the reversed spread angle formula. The spread angle theorem saying that you already have a triangle. If you already have a triangle, of course, BPC, the 3 points, they're collinear, right? They're on the same side. Then you'll be able to have such a relationship. Sine alpha plus beta over AP equals to sine alpha over AC plus sine beta over AB. Okay, this is our direct way. However, we can also say this reversely. If I can make sure I find 3 points, B prime, P prime, C prime, also make sure sine alpha plus beta over AP prime equals to sine alpha over AC prime plus sine beta over AB prime. Then I can claim B prime, C prime, P prime. These 3 points, they collinear. You guys follow me? So basically, this is the same theorem, but I want to say it from 2 different ways. Trust me, this is very important for North American competition. In the later lecture, we're going to talk about the Menelaus and the Siva theorem. These two theorems exactly has the direct theorem and the reverse theorem. Okay, within a triangle, you have 3 points. Okay, you have a Menelaus. However, if you have a Menelaus constructed within a triangle, then you can automatically say, okay, these 3 points collinear. Trust me, this might not be very familiar for our day school theorems, but this is very important for North American math competition. Okay, so far, so good? Okay, if all good, let's go to our last, not the last, like the second from the last. Okay, number 10. Number 10 is the famous Steward Theorem. Steward Theorem. This is a pretty nasty theorem, I gotta say. And but if you remember this theorem, it's gonna save your time significantly in the old math competitions. So let's check it out. Steward theorem per se is the condition is very brief. Given triangle ABC, P is a dynamic point on the BC side. Give a triangle, give you a dynamic point on the BC side. Okay, that's it. That's all the condition. The condition is pretty much nothing. Then you will have such a nasty thing. AP square equals to AP square, PC, BC. AC square times BP, BC. BC square times PC, BC, BP, BC. Try to remember this. Try to remember this. You have a triangle, and you just find a dynamic point on the BC side, okay? And nothing, that's it, all the condition. Then you will be able to determine the value of AP using what? AB, AC, BP, PC. So that being said, in a triangle, you have 1, 2, 3, 4, 5, right? In this 5 different segments, as long as you have 4, you'll be always be able to determine the last one. 5 segments, as long as you have 4, you can determine the last one, the 5th one. Okay. But after we see this, I think the first reaction is how are we going to prove this, right? Proving the Pythagoras and proving this, what should I say? This like Steward theorem, you really need a lot of calculation. But let me ask you a quick question. We're not going to prove it today, okay? But I'm going to ask you a question. Who can tell me this theorem, your first reaction, what kind of theorem we learned before looks quite alike such a theorem? It's time for you guys to do some guess. We have already introduced the last 9 different theorems, right? Is there anything looks quite similar, alike? We're not asking something super one-to-one mapping, right? But after you seeing this, do you have a feeling which kind of formula we learned before kind of similar to this? Yeah, I see many students, they give me the first reaction, cosine law. kind of like the cosine law thing, right? Yeah, if you can realize looks like the cosine law, you're 100% correct, because the proving process for such a problem is exactly using the cosine law. So this is something we need to talk about in our entire lecture. How can we solve a problem? As long as you solve a problem, how can you get started? Everything started by observation, right? Whenever you read a problem, whenever you see something, everything started from an observation. So if after the observation, you find something similar to this, in our case, it looks like the cosine law. Trust me, the similarity in a problem is always our breaking point, okay? As long as you see something similar to some formulas or some theorems, strategies you learned before, pretty much that's the breaking point for this problem. For our entire lecture, I'm going to be teaching you guys how to find out the similarity. You're not always getting this from inspiration or sparkling. There are some patterns. Try to remember the patterns and you'll be able to find out the similarity and find out the breaking point of the problem. Okay? So, like pretty much everyone mentioned in the group chat, this problem is similar to cosine law. And if you do some Google search, cosine law is the way how to prove this theorem. Okay? And there are actually another way how to remember this. This is pretty nasty, right? I think there's very difficult for you to remember. There's a shortcut how to remember this. I'll show you the shortcut. You can do something like this. If I have a triangle A, B, C, let's say this is A, right? This is C, this is B. Let's say this is M, this is N, this is D. Okay? So as long as you mark all the segments in such a way, you'll be able to get a formula like this. MAN plus DAD equals to BMB plus CNC. Okay? You basically do some simplification, you'll be able to get this. So how to remember this? There's a quick trick. You can say a man and his dad put a bomb in the sink. Okay? A man and his dad put a bomb in the sink. That's the way how you remember this Steward Theorem. Okay? Try to remember this. A man and his dad put a bomb into the sink. Okay? So far, so good? Okay. So, like I said, this is kind of too long, complicated thing, right? The Steward Theorem is too complicated. So even though you can't remember the entire Steward Theorem, I'm not blaming you, but there are 3 specific cases I think you guys need to remember. Okay, the generic Steward Theorem is kind of nasty, right? Like this. If you really have some problem, you cannot remember this, I'm not blaming you too much. However, there are 3 specific scenarios you'd better remember them. These are considered to be the simplified or specific version of our Steward Theorem. So this is actually our quick note. Oops. Quick note. What kind of specific situation you want to know in order to do this? There are 3 very important things. First, A, B, C. If AP is the bisector. Okay, for now, AP is the bisector. It's not a random, P is no longer a random point on the BC side. AP is a bisector. Here, please, this nasty long formula can be significantly simplified. So it goes to here. AP squared equals to AB times AC minus BP times PC. And this is the famous bisector length formula. AMC tested from time to time. How to determine the length of a bisector? This is the way. Bisector length formula. Of course, whenever you use this to, like the way how you determine this is going to be the combination between the virgin version, like the vanilla version, right? Like the vanilla version of this Steward theorem plus your bisector theorem. You combine them together, you get this bisector length formula. Okay, so far so good. Second very important case is here, A, B, C. Here, AP is the median. Like I said, if AP, they're just like random guys, no one cares, right? You don't have to remember. But as long as AP has some specific features, you need to remember. The first one is what? Bisector. Second one is the median of BC side. Here, you're going to have AP squared. Okay, this is the median length theorem. You see, as here, I think you guys might heard about the bisector length, right? You heard about the median length. Where those guys come from? They all come from the Steward theorem. Steward theorem is the prototype for pretty much all those fancy length theorems, so on and so forth. This is number 2 you need to remember. They were tested in the entire AMC or the Euclid history. Number 3. Number 3, we're no longer doing any magic for the P point. Number 3 is actually what? As long as my triangle, I'm going to do some magic for my triangle. As long as I have AB equals to AC. So this is what? An isosceles triangle. P is also dynamic. So this is the way how all the geometry works. You see, at the very, very beginning, the entire Steward theorem is pretty loose. The condition is pretty loose. Given a triangle, given a point. So you have very nasty condition. But as long as you strengthen your condition, the first way you do the strengthening is what? From P's perspective, AP is bisector, or AP is a median. But now I'm no longer struggling with P. I'm gonna make the condition like the strengthening for the AB and AC. Now P is still dynamic, but AB and AP become an isosceles triangle. I can also determine, change back the color. I can also determine AP squared equals to AB squared minus BP PC. This is also a very important property for our isosceles triangle. Isosceles triangle, you find a dynamic point on the BC side. You can always determine the length of AP using the same thing, AB, AC, BP, BC, blah, blah, blah. Okay? So far, so good? This is our number 10 theorems, the Steward theorem. Let's go to our last one, number 11. Number 11 is pretty understandable theorem, something like this. you have a quadrilateral, A, B, C, D. The diagonal of this quadrilateral are actually perpendicular to each other. So as long as you see this, the entire area of this quadrilateral can be 1/2 BD times AC. Is that right? The product of these two diagonals and then divided by 2. So far, so good? Okay, here I want to have another quick note. See, the very important thing is every time I'm going to give you some quick note, these are the extension of the problem or of the theorem, so on and so forth. In the entire math competition, as long as you see quadrilateral, regardless you're talking about the area or like any kind of weird properties, so on and so forth, your first reaction should be doing what? Let me ask you. As long as you see a quadrilateral in the math competition, what kind of property they ask you, whatever, your first reaction should be what? I don't know if you get this common sense from your day school or not. Probably not, but we'll see. As long as you see a quadrilateral in your problem, before you really go to there, you want to find out, how the tricks, what is your first reaction? Somebody says, draw a diagram, cyclic. Okay, these are, okay, these are pretty, it's pretty good. Yeah, this is pretty good. But actually, this shouldn't be the first reaction. Our lecture focus teaching you guys the conditional react. These shouldn't be the first conditional react. Your first conditional react, as long as you see a quadrilateral, your first reaction is actually conversion to triangle. Trust me, this is very important. Any kind of quadrilateral related problems, your first reaction should be converting them into a triangle. Trust me, this should be a very practical solution, practical reaction rather than anything else. Okay, because all those beautiful properties we learned so far for our entire high school geometry, similarity, congruent, Menelaus theorem, blah, 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 these are all based on triangles, right? None of them are based on quadrilaterals. So therefore, in your real math competition, as long as you see quadrilateral related problem, your first reaction should be break or convert the quadrilateral into triangle. Okay? All right. So that being said, we actually summarize all those important properties, right? And using this, we're going to use this as the, what should I say, like a guideline or criteria, okay? In the later part of our lecture, we're just going to do some discussion based on how to use all those technologies to solve some real problems. I'm going to give you some problems from a Canadian and American exams, so on and so forth. You can see how to dynamically using these problems. Okay, so far, so good? If all good, let's go to our real problems. This is the theorems, right? These are all the technology, the tools. Let's go to our real problems. The first problem, let's go for a Canadian problem. This is the old problem, 1998, Euclid problem. Let's have a look how you're going to solve this Euclid problem by using the technologies we just introduced. normally Euclid problem has multiple sub-problems, right? So let's go to problem number 1. These are easy problems. This is an easy problem. Euclid is for our Canadian math grade number 11 to number 12, right? So let's check it out, our first one. In the grid, you have a grid. So each small equilateral triangle has the side length 1. If the vertices of triangle WAT are themselves verticals of the small equilateral triangles, then what is the area of WAT? So the question asks you to determine what is the area for this triangle. What are we going to do for such a problem? How are we going to solve such a problem? Well, let's think about it. If I see the problem, my reaction should be basically go for this. First of all, my first reaction tells me this triangle is also equilateral triangle, right? Is that right? This is also equilateral triangle because they're pretty much everything is symmetric. So my question becomes, if I have a equilateral triangle with the size A, who can tell me what is the area of this equilateral triangle? What is the area of an equilateral triangle if the side is A? This is something you need to remember by heart. Okay, this is something you need to remember by heart. Under root 3, 4, A squared. Is that right? Any objections? How to do this? That's easy. You can what? 1 over 2, A times sine 60 degrees. This is 60, right? Using our formula number 2. Okay, this one is very important. Try to remember this by heart. Okay, so the $1 million question becomes how to determine A. How to determine A, I don't think that's that's like a mission impossible thing. Let's check it out from here. I'm gonna zoom it a little bit. Let's check out this triangle. This is A, right? This is what? 60 degrees, right? This is 1. This is what? 1, 2, 3, 4. This is 4. Then how can I determine A? Using what? Using what? I can determine the length of A. Please, everyone, participate. This is an easy problem. Everyone should know it right away, right? I have a triangle. I already know one side is A, the other side is 4. The included angle is 60 degrees. So how to determine cosine law, right? Cosine law. Cosine 60 degrees will be equal to 1 square plus 4 square minus A square, 2 times 1 times 4. Here you can determine the value of A, which is under root 13. Right? As long as you know this, put it here, you figure out the area of this equilateral triangle, which is 13 over 4 under root 13. That's it. So every single step, you can't think too much, right? You must use our intuition, every single one. We see this equilateral triangle, automatically figure out the area of this should be using under 3 over 4A squared. If you don't know for now, no problem. We're going to do that. Root 3? Oh, yeah, root 3, yeah. Sorry, not root 3, root 3. And second conditional react, as long as you see like a weird thing like this, your first reaction is doing what? Actually you can directly use the cosine law, right? Use the cosine law, you get the answer right away. So this is an easy peasy one. Even though it's a Euclid, using the technology we introduced, you do it right away. Okay, let's go to our second problem. You have a triangle ABC. M is the point on the BC such that BM is 5, MC is 6, AB is 7, AM is 3. The question asks you to determine what is the value for AC. What kind of technology I need to use? Directly Steward, right? We directly use the Steward Theorem, right? We introduced it to, like the Steward, they should be able to use here right away. So, AM square, 1 over 2, AB square, 1 over 2, AC square minus 1 over 4 BC square. Directly using our Steward. And you can see AC equals to 27. Under root 27. So far, so good? See, using the technology we introduced, we solved this Euclid problem in about 30 seconds. I mean, not to say the calculation, but like thinking-wise, only 30 seconds. This is an easy peasy problem. All right, so far so good? Okay, let's go to our second problem. Second problem is something like this. Q2. In the given triangle, ABC, D and E are both midpoint of AC and BC. BF equals to 1 over 3 AB. Okay, two things. First one, proof GE is parallel to AC. Second one, determine the value of triangle BFG's area and triangle BEG's area. I'm going to give you the graph here. Yeah, something like this. This is A, F, B, E, G, D, C. Okay. Let's check it out from here. So you have a triangle. So in this triangle, you can see that D and E, they are both the midpoints. AD is equal to DC, BE equal to EC. And the BF is actually 1/3 of AB. Okay? With this information, the question asks you to prove two things. First, GE must be parallel to AC. Second, determine what is the area ratio between BFG and BEG. Okay, let's focus on the first question, like the first part. How to prove GE is parallel to AC? So we're actually teaching you guys the thinking process. How do you think whenever you see such a problem? This is extremely important. The question gives you a weird thing, something like this, right? And you have some midpoints and you have like a 1, BF is 1 over 3 of AB. And then at the end of the day, the question asks you to prove GE is parallel to AC. Okay, if GE is parallel to AC, what are you gonna have? If GE is parallel to AC, then automatically BG will be the same BG will be the same as GD, right? Okay, so it looks like your $1 million question is that we want to prove G is the midpoint of BD. Okay, G is the midpoint of BD. If you want to prove this, like I said, you actually see G. Where is G? G is actually one vertex of this AFGD. This is kind of like a quadrilateral, right? Of course, I won't be able to do all my tricks in the quadrilateral, so I must put it into a triangle, right? This is our thinking process. I need to construct a triangle. This is my goal number one. And the second thing, do you see a weird thing like this? BF is 1/3 of AB. We're not really liking 1/3, right? All our theorems teaching me is pretty much the midpoint. That's it. We talk about the median, right? We talk about like bisector, bisection. We never talk about trisection, right? Or some like the 1/3 point of the entire segment. So that being said, I'm kind of need to construct a median point, right? As long as I have something medium, then I'll be able to do my magic and figure out the things. This is the thinking process. First of all, I want to create a triangle because all the magic happens in a triangle. Second, I must create a medium because all those like a middle point is gonna solve all the problems one by one. Plus, I don't really like this 1/3 thing. I like 1/2. So with all those information, who can tell me what is the most straightforward way or the most intuitive way to create this auxiliary line? We're probably going to create some auxiliary line, right? What is the most straightforward way to create auxiliary line? Yeah, I see somebody has the correct answer. Very intuitively, the auxiliary line is you want to find a midpoint of AF. I put it at H. Find midpoint of AF. Let's say AH equals to HF, right? And then connect HD. Why? Because by doing this, I've actually figured out two things. I'm already construct a triangle. So my BD becomes what? My BD becomes one side of my triangle BHD, right? And second, for some reason, I figure out, okay, these three parts, they're all the same. So AKA what? Means the entire thing, I'm gonna have some midpoints. F becomes the midpoint of BH. Is that right? This is the thinking process. Why you want to do this? You do this for a reason. As long as you know this, I think the entire process becomes so easy because intuitively, you're gonna have what? H is the midpoint. So what are you gonna have? BF equals to FH, right? Because BF is 1/3 point and H is the midpoint of AF. So the entire thing, you're gonna have BF equals to FH. And at the same time, you're gonna have what? This is HD, for instance. These are the HD. You're gonna have AD equals to DC. These two conditions put together, you're gonna have HD is actually parallel to FC. Right? I'm gonna use different color. HD is actually parallel to FC, right? Okay, here you also have BF equals to FH. Put them together, BG must be equal to GD, right? BG equals to GD. As long as BG is equal to GD, don't forget PE is equal to EC. Then GE is parallel to AC. That's it. Okay, try to learn from my way. Do not use a long thing. Only 3 lines, right? This is 1, this is 2, this is 3. 3 lines, you get what you need. Do not use a long explanation process, take you forever. Try to do something like this. 3 lines, you get what you need. Okay? So far, so good? Okay, let's go to our second part. Second part, I think second part I have to rewrite it one more time. Second part is very interesting. I like to take this opportunity to show you guys some important way how to think. This is here. This is here. Okay. A, F, B, E, G, D, C. The question asks you, what is the area ratio between this black triangle and this red triangle? Okay. You are trying to do an area ratio between these 2 triangles. Okay? And normally speaking, if you want to do an area ratio, you want to have either they share the same bottom, right? Or they share the same height. Then you'll be able to do all your magic, so on and so forth, right? But this time, these 2 triangles, I don't think they share the same bottom or they share the same height. Yeah, of course you can say they share the same bottom, but that's going to be something you have to do something like this, eh? It's pretty weird, right? I don't think that's a good way. So maybe directly using the formula, this is not something so doable. This is one thing you need to think about it. Is that right? You guys follow me? Because these 2 triangles, they're not sharing this, they're not sharing everything. I mean, they're not sharing anything. They just like kind of tilt there. As long as you see such a problem, in the North American math competition, there is a common strategy to solve such a problem. Okay, 2 triangles, you want to do this area ratio, area 1 over area 2, right? And these 2 triangles, they're not sharing anything. They're basically in the middle of nowhere. As long as you see this, the Kangman Rule, Kangman strategies, you need to find a middleman. You need to find a middleman. Okay? This middleman must have the relationship with triangle number 1 and also have relationship with triangle number 2. And then you kind of like consolidating this relationship between these 2 things, and you will be able to get the relationship between S1 and S2. Okay? Find a middleman. You somehow find out S triangle 1 is m times of this middleman. S triangle 2 is n times of this middleman. Then, of course, S triangle 1 over S triangle 2 will be m over n. You guys follow me? This is a common strategy. Try to remember, this is a very important common strategy. Well, as long as we know this, I think intuitively everyone will ask me the same question. How can you find a middleman, right? How can you find a middleman? So finding a middleman is actually very important, right? The $1 million question is trying to find a middleman. But how to find your middleman? The middleman always gets started with your neighbor all the way to as big as possible. Conclusion. How to find a middleman? Start from your neighbor and with the largest triangle. This is a very important thing. We want to use the simple problem to denote this very important theorems. Whenever you find a middleman, you want to do comparison, right? You want to have some relationship between this middleman. But how can you get started? You always get started with your neighbor. And then gradually, maybe you're going to find a guy in your neighbor, and then across the street, and then cross 2 blocks, and all the way your entire community. You always start with your neighbor. And then you always stopped or ends with the largest triangle for the entire shape. Okay, why? Because your neighbor is easy, right? You start with your neighbor, you can find a relationship. And why you stop with the largest one? Because the largest one is everyone they can touch. Every single triangle, at the end of the day, they could be able to have a relationship with the largest triangle. Okay, so this is basically how it works. If that's the thing, let's focus on this problem. I'll show you how to do this. Okay, so I'm gonna get started with this. Like I said, we want to find a middleman, right? If we want to find a middleman, we're gonna do something like this. Okay, I'm just gonna G, change the color. This is gonna be G, this is gonna be F. Okay, let's say I say my triangle BFG. The area is A, okay? At the very beginning, the area is A. I want to get started with my neighbor. Triangle BFG has 2 neighbors. One neighbor is actually BEG. This is what you are asking for. Of course, you cannot start with them, right? The other neighbor is what? Is this equilateral, is this quadrilateral ADGF. Is that right? Do you still remember what I mentioned? You can never do anything with any quadrilateral. Always convert quadrilateral into what? Into a triangle. Right? Every single step is what we introduced. So intuitively, you're going to put an auxiliary line to create a triangle. Okay, so let's get started. If my triangle BFG has area of A, so this red triangle is going to be area of 2A, right? This is going to be 2A. You guys follow me? Because they share the same height, while the bottom is 1 to 2. Okay, you reach out your neighbor, right? Moving forward, let's check out this triangle. This triangle is what? Has an area of 3A, right? And this triangle and this green triangle, they should have the same area, right? Because we just proved G is the midpoint of BD in the previous question, right? G is the midpoint. So you're making your neighborhood a little bit wider. So this is going to be 3A as well. Is it good? Okay, don't stop. Keep going. Now, the red triangle becomes what? 3A plus 3A, 6A. This red triangle should have the same area with this brown triangle, right? So this is also 6A. So always start with your neighbor, then gradually, at the end of the day, you want to take over the entire community, right? Like you are doing some, some camping, right? You want to at the very beginning, you want to go to your neighborhoods, right? And then go to one state, the other state, and the entire south and the north, so on and so forth. Same strategy. So that being said, the entire triangle ABC will be 12A. Okay, so far so good? Very understandable, right? Okay. If you finish this, if you understand this, I'm going to erase it. Who can tell me how to find out the relationship for this guy? A, B, E, F, G, C, D, right? Our previous discussion already reviews triangle BFG is 1/12 of the big triangle ABC, right? This part is done. Now, we're going to focus on this part. I need to figure out the triangle BGE is how many percentage of triangle ABC. And then I just do whatever I mentioned here, right? I get what I need. So, quick exercise time. Who can tell me what is the area ratio between triangle BEG and the big triangle ABC? Yeah, I see many students have the correct answer already. Yes, that's exactly the same strategy, right? You need to learn this strategy. Again, I'm going to take this part as what? B, right? If this is B, you want to start with what? With your neighborhood. Automatically, you want to connect the DE, right? In order to make your neighborhood. This is B. This is also B. So for the entire triangle here, the blue triangle, you're going to have 2B, right? Because E is the midpoint. So the blue triangle and the green triangle, they have exactly the same area. So this is also 2B. So that being said, for this brown triangle, this is going to be what? 4B, right? And the brown triangle, they have exact, let me change the color to maybe black. The brown triangle should be exactly the same area of this black triangle. So this is also 4B. So the entire triangle will be what? 8B, right? The entire one will be 8B. So that being said, your triangle BEG will be what? 1/8 triangle ABC. Is that right? So if you want to do an area ratio, you just ratio left equals to ratio right directly to 3 to 2, right? 2 to 3. Yeah, 2 to 3. 2 to 3. That's the solution for this problem. Try to remember this. AMC test it from time to time. Always do the area ratio from your neighborhood all the way to the entire big triangles, and you're good to go. All right? So far, so good? Okay. before we move forward to the next question, let me ask you another quick question. If I see this problem in AMC, do I have to use the same thing? The entire thing? Or you have something even faster? So this is what I want to teach you. Always fast track for AMC. For our Canadian exams, you have no way. You have to follow exactly what I mentioned previously, right? There's no way around. You just have to do this. But for AMC is a multiple choice. Who can tell me, do I really have to go for such a long process? Can I do something faster and get something right away? This is another very important thing I want to show you guys. Fast track for AMC. The question says, okay, in this question, the question says, given a triangle ABC, right? They find all those B, F, E, G, whatever points, so on and so forth, right? I don't really care. And then you do your calculation. If given the triangle means the question has no constriction for this triangle itself, right? It works for all the triangles. So if this is AMC, you just let triangle ABC is what? A equilateral triangle, and that's it, right? Any triangle works, so my equilateral triangle should also work. You guys agree with me? Right? If that's the case, okay, then your problem becomes super straightforward. If this becomes an equilateral triangle, don't forget, D is the midpoint. So here becomes what? Bisector, right? And the other thing becomes something like this. You are trying to determine the area ratio between the green one and the red one. Okay, you know what? Don't waste your time directly using our second method. This is B, F, E, G, for instance. Then triangle BFE over triangle BEG will be what? 1 over 2 BF. BF is actually 1/3 of AB, right? BE, I don't really care what BE is. Sine 30 degrees. 1 over 2 BE, I don't really care what BE is. BG is like 1 over 2 of our side, right? And then still sine 30 degrees. Cross, 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 and cross this, still 2 over 3. You solve this problem in about 30 seconds. You guys follow me? Okay, if you see this problem in AMC, don't waste your time doing the calculation, trying to do such a thing. And this is actually a very important mathematical thought. This is actually enrichment. Enrichment. In the entire world of mathematics, as long as you see some very complicated problem, maybe at the very beginning, there's no way for you to solve them, but you can try to enrich the condition. Like our gold box conjecture. In our almost like all this like 100 years, right? No one knows the solution, but we can keep enriching. If I cannot solve this problem in a real triangle, in a random triangle, what about I start with an equilateral triangle? What about I start from equilateral into an isosceles triangle? And what about I go to a acute triangle? I can gradually, at the very beginning, have a very strong condition, but gradually, I make it more loose, right? You can actually make this conclusion more generic. Okay, so far, so good? Try to understand this part. This is extremely important. Doing some enrichment. Okay, doing some enrichment. If you're not so sure, try to make it enriched. Put it into the equilateral triangle. This is going to solve this in 30 seconds. This is an important strategy I want you guys to understand. So far, so good? Okay. Next problem. Our problem is becoming more and more difficult. Number 3, let's have a look at it, AMY problem. This is the graph of this problem. I'm just going to drag this. Yeah, this is a problem from. This is also an old problem, 1989, AMY number 15. The last problem for AMY. But these days, I think they're like the middle level. They're, you know, the AMY's complexity has become bigger and bigger. I think for now, this is going to be a medium level problem for AMY. Let's check it out. Again, I want to show you guys how to think for such a problem. Okay, I'm going to put it here. And then you cut it. That will be good. All right. So the problem says something like this. You have a point P inside a triangle ABC. Oh, those are actually like the different lines. There's no condition. You just basically find the different points. Okay, the question gives you some lengths of the size. AP is equal to 6. Oops. BP is equal to 9. PD is equal to 6. Okay, then that being said, P is actually the midpoint of AD, right? What else? PE, P equal to 3. CF, the entire CF equals to 20. With all those information, the question asks you to determine the area of triangle ABC. The entire area of triangle ABC. So, as long as you see such a problem, again, I'm going to be asking you guys, what is your conditional react? How do you want to get started? The question gives you a bunch of lengths for all those segments, right? So on and so forth. And the question asks you, what is the area of the entire ABC? Let me ask you a very low-key question. Okay, if you are in the middle of the exam, you see this problem. You see the question gives you a bunch of side lengths, right? There's nothing but side. And at the end of the day, the question asks you to determine the area of this triangle. Who can tell me intuitively, whenever you see this, what is your first reaction? What kind of formula or technology you might use in order to solve this problem? So this is actually a very important common sense I'm helping you guys to build up, okay? By reading this question all the way to here, the question gives you a bunch of sides, A, B, B, C, C, A, blah, blah, blah. At the end of the day, the question asks you, okay, what's the area? I'm not asking you how to do this. I'm just asking you, generally speaking, the big direction. Who can tell me? What is the big direction? How to? What kind of technology we might use to solve this problem? This is actually our step number 1, right? Our step number 2 is how to do the auxiliary line, how to blah, 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 do everything. But just forget the cut the relative stuff, right? We just directly go to the solution. I mean, go to like the very big direction. Who can tell me what kind of technology I might use to solve this problem? I see someone has the correct answer. Heron's formula, right? Only Heron's formula, those kind of P minus A, P minus B, P minus C, right? P minus C. Only this Heron's formula gives me a flexibility to directly determine the area from the size. You don't even have to have the sine, cosine. You don't even have to draw the height. You directly form it. Are you guys all agree with me? Yes or no? Can I have some feedback? Can you put something into the group chat? Yes or no? So this is actually what? This common sense. So this sense should be gradually built up by your exercise. Practice makes a perfect, right? Makes perfect. So this is actually what you want to do. Big direction, Heron's formula. Okay. Second thing I want to ask you. By reading these numbers, 6, 6, 3, 9, do you find anything kind of inharmonic? You know, simplicity is beauty, right? Beauty exists in harmony. By reading this number, do you find anything kind of like inharmonic and give you kind of like what should I say? Just give it like a tendency, right? And you can't stop yourself thinking about something. Is there anything you can find out like that? 6, 6, 3, 9. Pretty. At least whenever I see this problem, I have this feeling right away. Something in this graph makes me very uncomfortable, and I want to break it. I want to fix it to make myself comfortable. Because think about this, and this is actually my feeling. Think about this is actually 6 to 6, kind of like a midpoint, right? However, this is 3 and 9. This is not a midpoint, right? If I can do some magic to construct out another midpoint or something, I may be able to use kind of flowery things to make things happen, right? All those I really love midpoints, right? I hate the other 1/3 point. It doesn't make sense. So that being said, if for some reason I can figure out another, maybe, I don't know, another point, make sure this is also 3. So this is going to become 6, right? So I'm kind of having a lot of like harmonic in my graph. Do you guys agree with me? If I can do some magic, make it happen, I might be able to find some harmonic in this. These are the thinking process. Why you're doing this? Why you want to add this auxiliary line? There might be some reason. And the third thing is, the question gives you a bunch of midpoints, and you look the graph. It looks like CD and DB. It's also the same. It looks like, but there's no guarantee. You have to prove it. So it looks like CD and DB, they're also kind of, D is also a midpoint, right? So these are all like those kind of like what should I say? Information, like the pieces of information scattered all over the place. But you gotta have like a conditional react or kind of like a hint by all those pieces informations. So if that's the case, when you're gonna solve this problem, you're gonna do such a way. From D, you want to make 2 parallel lines. DQ parallel to AB and DM parallel to AC. DQ parallel to AB. DM parallel to AC. Let's check it out. Why I'm doing this, you're gonna see this gradually by gradually. AP equal to PD, right? This is given by the question. DM is parallel to AC. This is exactly what you just created. All of this together, you're gonna have EP equal to PM equal to 3, right? This is exactly what you want, right? Because this is the midpoint, and this line, oops. I want to use this. Okay. I'm going to use another line. Okay, 1 sec. This guy is parallel to AC. AP is equal to PD. Of course, EP will be equal to PM, right? Okay. Don't forget, MD is also equal to AC. So that being said, you can say that D is the midpoint. Is that right? Of CB. Because what? EP is the same as PM as 3. So M actually becomes the midpoint of EB, right? MD is also parallel to AC. Of course, CD becomes the same as DB. CB, CD is the same as DB. As long as CD is the same as DB, you're going to do the strategies one more time. Okay, QD is parallel to AB. So therefore, Q is the midpoint of CF. Is that right? Okay, luckily everyone is the midpoint. You see? Finally, everyone is the midpoint. That's actually a very good news. That's actually a very good news. So, okay, so that being said, Q is the midpoint of the entire CF. Okay. AP is the same as PD. QD is parallel to AB. So that being said means what? QP must equal to PF, right? These two parts must be the same because these two triangles actually, oops, go back. So actually these two triangles are actually what? Congruent to each other, right? So QD is the same as PF. So that being said means what? The entire thing is what? The entire thing is 20. So this is going to be 10. This is going to be 5. This is going to be 5. Is that right? Every single step is kind of very reasonable. Okay, now you actually figure out pretty much all the formulas for everything, all the lengths for everything. The question is asking you what? The question is asking you what is the total area of the entire triangle ABC? The entire triangle ABC is kind of like difficult. In order to do that, you have to figure out all the sides. For now, you kind of like know nothing, right? You know nothing for the entire triangle. However, as long as you find a bunch of midpoints, let's say this is midpoints, right? This is the midpoints. This is the midpoints. Maybe, let's say something like this. If I will be able to figure out a area of a small triangle, and then just use the technology we introduced in the previous question, we find an area ratio to its neighborhood, and then a larger neighborhood, and then a larger neighborhood. At the end of the day, I will be able to take over the entire community. I will determine the entire area of triangle ABC. You guys cool with me? This is like the way all the problems that are actually connected. We introduced the problem previously. Now we're going to we introduced the technology in the previous problem. Now we're going to use this problem right away in this. So I can't directly go to ABC, unfortunately. But I can gradually, right, doing this from a small triangle, like the green one, and then to the bigger one, and then to the bigger one, so on and so forth. Okay. So let's focus, let's do $1 million question. How can I figure out the area of the screen triangle? How can we determine the area of the screen triangle? Let's check it out from here. We already know, right? This side, like something that I know, I just make it as mark, as red, right? This part is already know. This is what, 15, right? This part I know. This is 6. This part I have no idea. I'm just gonna put it as black. X, right? What else? I think for this green triangle, I have nothing to say. That's it. But if I check its neighborhood, this part I already know. This is 9, right? This part I don't really know. But this is also X. Okay. That being said, think about it. If I want to have a close look at these two triangles, like the green triangle and this white, I mean like red, excuse me, I speak Chinese. Red triangle. I heard that there's a joke recently, like a Chinese professor or something like in the States, and when he got a little bit confused, he keeps saying neg, and he got a complaint from a specific community saying that he's racist because he used the other word. Okay, so you know, but our candidate is like better, right? So that's like a joke I heard about from what is called like YouTube or something. Okay, so let's continue. So my goal is trying to determine the area of my green triangle, right? As long as I have it there, I'll be able to go all the way, determine the big triangle. Okay, and how can I do this? I think this is something quite doable because my green will be the same as my red, right? These two triangles, because D is the midpoint, these two triangles, they share the same bottom, like the same latitude. So triangle red. Okay, how to determine the area for this green triangle? You have to determine the P. P is actually 15 plus X plus 6 divided by 2. And then you're going to do this P minus A, P minus 15, P minus X, P minus 6, right? What about this red triangle? You also have to determine a P prime. This is going to be 6 plus 9 plus X, right? This is 6, this is 9, and this is X. And this area is going to be P prime minus 6, P prime minus 9, P prime minus X. Is that right? This is going to be a formula. This is actually using our Heron's formula, right? Like somebody mentioned, Heron's formula. And this equation is going to be nothing but a gigantic equation talking about X with a lot of underscore nasty things. But nevertheless, you will be able to solve it. It's only one variable, this one equation, you will be able to solve it. And I'll tell you the value as equals to 117 under root. Okay, as long as you know the value for X, you will be use this Heron's formula, either of this Heron's formula, you will be able to determine the area of this green triangle, right? This is exactly what we want. I'll show you this value right away. This is actually 27. The area of this green triangle is 27. Okay, but your goal is not to determine this green triangle, but the entire big triangle. That is exactly the same as our previous question. This is 27. Let's try to use A. I think ABCD is actually easier, right? If this is A, let me try to use different color. If this area is A, so the black triangle will be exactly the same as A, right? Because this is the midpoint. And then this big green triangle will be what? 2A, right? Again, D is the midpoint. So the entire triangle will be what? 4A. Is that right? So the total answer will be triangle green times 4 will be your direct triangle ABC. Is it correct? All the way, your big triangle becomes 108, which is the answer for today's problem. Okay, Amy is always the integer from 0 to 99, right? Okay, so that's it. That's all what I want to say for this problem. Okay, any questions so far? Let's do a quick recap. Today, we introduced 11 different rules integrated into our area method, right? And we actually introduced some very important technologies, how to doing the ratio, right? From here to the neighborhood all the way to the big one. How to basically do the auxiliary line, how to find out the midpoint. Everything comes from the inharmonic, right? Auxiliary line is helping break this inharmonic, make it harmonic, right? And then we introduced a bunch of ways how to, how to determine, how to simplify the problem by enriching. If in AMC, this is like not necessary you do it from A to Z, you can actually enrich it. So hopefully all those technologies you can try to understand, okay? We have a limited lecture, but we try to give you as much technology as possible. In today's homework, we're gonna give you 3 problems using this technology. And in the next lecture, we're gonna give you guys more complicated problems, okay? How to use the area method. So the area method, we're gonna go for 2 lectures. Okay, that's pretty much what I want to say for today's lecture. You have any questions for me? All good? Okay, perfect. In that case, I'll see you guys next time. Hope you guys enjoy the rest of the weekend. Bye, guys.